All right. So chapter 14, all about integrals. So we just spent all of chapter 13 essentially talking about derivatives of multivariable functions. So what we're going to do in chapter 14 is try to make some sense of integrals of multivariable functions. And we got a kind of a preview. If you looked at the bonus question that was on the second part of the test on Friday, it had to do with integrating a multivariable function. So that was kind of a preview of what we end up doing. For now, what we're going to do is in this chapter we're going to focus only on definite integrals, because when we integrate a multivariable function, the constant of integration can be a function of one of the variables that we're not integrating with respect to. So x is constant with respect to y, and y is constant with respect to x. So for now, we're just going to look at definite integrals. So what I want to do is do a couple of examples, talk about how we do them, and then we'll give a geometric interpretation to what we're talking about. And then we spend all of chapter 14 applying that idea to multiple integrals in various contexts. All right, so let's look at the integral from e to the y to y of y natural log x over x dx. And we're going to say y is greater than 0. So for this particular integral, x is variable and y is constant. So we treat y just like we treat a constant in any other integral. And our limits of integration are functions of y. So they're constant with respect to x. They're constant. Our limits of integration are constant with respect to our variable of integration. And I'm just going to write our WRT with respect to. So our y is constant and our limits of integration are constant with respect to our variable of integration. So let's evaluate this integral. I'm going to factor out the constant, and we have y integral e to the y of y ln x dx. And how are we going to evaluate this integral? What does this evaluate to? Natural log x squared over 2. U is natural log x, du is 1 over x dx. So this is going to be y over 2 natural log x quantity squared, and we're evaluating that from e to the y to y. Everybody follow on the evaluation of that integral. So we're going to be doing a lot of integrals, so all of our integration techniques, all of those lovely things that we've learned about evaluating integrals. Talk about those a lot in this chapter, in the next 2 chapters actually. All right, so then we plug in our limits of integration. So this is y over 2, natural log of y squared, and this is going to be out here, minus natural log e to the y squared. And we simplify this to just y over 2. This one won't simplify, natural log y squared minus y squared. And that's our That's our answer. So the result of evaluating this integral with respect to x is we end up with a function of y. And y is constant with respect to x. So we just treated y as a constant. Are we good with what we did there? All right, let's look at another example. So this one we're going to go from 0 to x to the third of y e to the minus y over x dy. Here y is the variable. X is constant. So this x up here in the exponent, that's just a constant. We don't have to worry about that when we're evaluating our integral. All right, so we're integrating y, basically y e to the minus y. What do we need to do to integrate that? Parts. We need to use parts. Integration by parts. I'm going to let u equal y. du is dy. And I'm going to say dv is e to the minus y over x. And v, I need to integrate this, e to the minus y over x, and x is a constant. We're integrating this with respect to y. So when we integrate this with respect to y, what do we get? Minus x e to the minus y over x. X is just a constant. So it would be just like integrating e to the minus y over 2 with respect to y. And you can check, just like we always did before, check by taking the derivative of this with respect to y. All right, now we're ready to keep up with our integral. So I'm going to leave off my limits for now for the intermediate steps of doing the integration by parts. So the integral of y e to the minus y over x dy is u times v minus xy e to the minus y over x minus the integral of v du. So we get a minus x e to the minus y over x dy. Now we need to evaluate this integral. So what are we going to do to evaluate this integral? We're evaluating this with respect to y, so x is constant. So I can just say u equals minus y over x. Du is, with respect to y, du is minus 1 over x dy. So I have e to the u du. So this evaluates to, everybody with me there? This evaluates to, we end up with the minus xy, e to the minus y over x. And this, I need to leave my negative sign here because my negative inside comes from my du here. So I end up with minus x squared e to the minus y over x. And now we need to evaluate this on our limits. So we're going to put our limits in here, 0 to x cubed. And we get, when I finally evaluate this out, I'm going to just write all this out. We get minus x to the fourth, e to the minus x squared, minus x squared, e to the minus x squared, minus, and then for my 0, 0 minus x squared, just writing all this out. And I get finally, when I simplify this, x squared times 1 minus e to the minus x squared, minus x squared, e to the minus x squared. So my function, when I evaluate this integral with respect to y, I end up with a function of x. So in each of these examples, now we could integrate this function with respect to x. So we evaluated one function with respect to y. We did one integral with respect to y, ended up with a function of x. Now we could evaluate this, we could integrate this function with respect to x. In our previous example, we evaluated an integral with respect to y, and we ended up, with respect to x, and we ended up with a function of y. We could then integrate this with respect to y. So we could end up evaluating our integral with respect to x and then with respect to y. And for this other one, we could evaluate this with respect to y and then this with respect to x. That kind of leads us into this idea of an iterated integral, where we can evaluate an integral with respect to one variable and then turn around and evaluate the result with respect to the other variable. So that's where we're going to go with this idea of holding one of our variables constant. We're going to do this iterated integral. We're going to integrate with respect to one variable and then integrate with respect to another variable. So is everybody with me so far? More or less? Okay. All right, so let's look at an iterated integral. So an iterated integral looks something like this. Integral from 0 to pi, integral from 0 to sine x of 1 plus cosine x dy dx. So this would be an iterated integral. We do these inside out. So what I'm going to do is evaluate the inside integral first. So I evaluate this integral with respect to y. I end up with a function of x, and then I'm going to evaluate the result, the integral of the result, with respect to x. So our inside limits of integration are constant with respect to the inside integral. Our outside limits of integration are constant with respect to both variables. All right, so let's do the inside integral first. So I'm going to leave my outside integral written here. Integral from 0 to pi. What's the integral of 1 plus cosine x dy? X is constant. What's the integral of 1 dy? Y. X is constant, so cosine x is constant with respect to y. So what's the integral of cosine x dy? Cosine x is just constant. So what do we get? What would be the integral of 2 dy? 2y, right? So it's not cosine xy, it's just y cosine x. Cosine x is just a constant with respect to y. And we're evaluating that. All right, everybody see that? Cosine x is constant with respect to y. That's just a number. We're evaluating that from 0 to sine x, and then I still have my outside integral. So when I evaluate this integral from 0 to sine x, I end up with my outside integral is 0 to pi, and I get sine x plus sine x cosine x dx. And now I'm integrating with respect to x. My inside integral gave me a function of x. Now I can evaluate this integral with respect to x. And this one, hopefully, should be easy. What is it? So what does this integral evaluate to? Sine x dx, integral sine x dx. Negative cosine x? Yes. And sine x cosine x? Let's let u equal sine x. Du is cosine x dx. So what do we get? Sine squared x over 2. And we're evaluating that on 0 to pi. And we get a negative, I'm going to put all my pieces in here, negative 1 plus 0 minus negative 1 plus 0, and this equals 2. So the integral from 0 to pi, 0 to sine x of 1 plus cosine x dy dx is 2. So when we evaluate an iterated integral, you evaluate it inside out. Do the inside part first, and then the outside. The inside integral gives us a function of the outside variable, and then the second integral gives us a real number. The inside limits of integration can be variable with respect to the outer variable. The outside limits of integration have to be constant with respect to both variables. All right, questions on what we did there? So doing this type of integral is the kind of the essential tool. This is what we'll be doing for the entire chapter 14. This type of thing. And in just a minute we'll apply a geometric idea to what this is telling us. All right. The union of the variables, the two intervals of integration, is called the region of integration. And we're going to be talking about the region of integration a lot in chapter 14 as well. And usually we call it R. So in the last example, our region was 0 less than or equal to y less than or equal to sine x, union 0 less than or equal to x less than or equal to pi. And if we were to draw just quickly, a little sketch of our region, from 0 to pi, y is going between 0 and sine x, so we're looking at that region in the xy plane. Y is between, and this is y equals sine x. Y is between 0 and sine x, and x is between 0 and pi. So that would be our region of integration. So finding our regions is going to be an important important tool, we'll use the limits of integration on our integrands to figure out what our region is. We will have to set up integrals and set up our limits of integration when we're given a region. So this idea of the region of integration is another important idea in chapter 14. All right, so let's talk about what we're talking about geometrically here. So the easiest idea of an iterated integral is going to be something very familiar. The area of a plane region. So the reason we're talking about this now, I want to give this idea of the area of a plane region, interpreting an iterated integral as an area of a plane region that's familiar, and it'll give us a starting point to do some more complicated things with our integrals. So let's look at a region in the xy plane bounded by two curves. So let's say we have two functions, and we'll call this g2 of x and this one g1 of x. And we're going from x equals a to x equals b. So we want to find the area from a to b between these two curves. Now we know how to do that. We have a technique for doing this using a single integral. But I want to give this interpretation to an iterated integral to give us something familiar to kind of pin our ideas to start out with. So we want to find the area between g2 and g1 from a to b. So what we're going to do to give this interpretation to our iterated integrals, I'm going to divide this into tiny little rectangles. And the thickness of that rectangle is dx. And what we're going to do is find the area of a single rectangle, a single one of these rectangles, by integrating. So I'm going to find the area of one of these rectangles by integrating. So for a particular x, the area of one rectangle and we're saying x is fixed, x is constant. A for this one rectangle is going to be the integral from g1 of x to g2 of x dy. So I'm dividing this tiny little rectangle into little slivers, and I'm stacking those little pieces on top of each other and summing those up for y goes from g1 of x to g2 of x for a particular value of x. And when we evaluate this integral, this gives us y evaluated from g1 of x to g2 of x, making all the steps explicit here, which is g2 of x minus g1 of x. And then we're going to add the area of all of these individual rectangles together for x equals a to b. So to add those together, I'm going to integrate from a to b of g2 of x minus g1 of x dx. Does that look familiar? That's the area between two curves, the integral that we did for the area between two curves in Calculus 1. Well, we got to this by evaluating the integral with respect to y first. So we're going to combine these two as an iterated integral. So we could say the area is the iterated integral, the double integral, the integral from a to b, the integral from g1 of x to g2 of x, dy dx. So this is a geometric interpretation of this iterated integral with no function inside, just an iterated integral dy dx. That's the area of this plane region. And after we evaluate this first integral, it turns into our familiar integral that we use in Calc 1 to find that area. So that's how we're going to interpret this iterated integral geometrically. We'll start putting functions in here, and we'll let the functions be different things, and we can find surface area, we can find volume, we can find moments of inertia, we can find the centroid, we can find all kinds of different things by putting functions in here into this iterated integral for this particular region in the plane. It's kind of nice. We'll be able to find, remember what we had to do to find the moment of inertia or the centroid of a planar lamina. We had to make all kinds of assumptions about where the mass was concentrated and that kind of thing. With an iterated integral, we don't have to do any of that. We can just evaluate a double integral directly, and we're set. It's kind of nice. All right. If our function or if our region is bounded by curves rather than above and below on the left and the right, then we can write our iterated integral in just a slightly different form. So our region for this particular example, our region is bounded on the left and right by functions of y. So for this particular region, and we will do integrals in both ways. It just depends on how the problem is presented and how we set it up, and sometimes we can choose how we want to do it as well. So if we have some function of y, so this is h1 of y and h2 of y, just like we did before, and we're going from C to D, y equals C to D. This time we're going to draw our little rectangles, and let me do that in red. Draw our little rectangles horizontal. And this thickness of our rectangle is going to be dy, and we say the area is the integral y equals C to D of the integral of x from h1 of y, h2 of y, dx, dy. And our integral, we evaluate our integral in the opposite order. And sometimes, depending on the problem, depending on how the problem's set up, how we're given our region of integration, it will be easier to evaluate our integral in one order than the other. Sometimes it'll be impossible to evaluate the integral in one order, but if we switch the order and take care of our region, how we set up our region, then our integral then becomes possible to evaluate or easier to evaluate. So we're just turning things in the opposite order. We have our function set up this way. And we call the first case where we set our little red rectangle, we set that as a vertical rectangle. We call this kind of region vertically simple. I'm just going to write that here in red. This is a vertically simple region. So when we draw representative rectangles vertically, we call it a vertically simple region. And when we draw representative rectangles the other way, we call it a horizontally simple region. And the textbook you'll read, they'll talk about vertically simple or horizontally simple. They'll use that in the context of problems. So all their meaning is, are you setting your representative rectangle vertical or horizontal? And sometimes you'll have a choice. How do you want to set it up? Do I want to set my rectangle vertical, horizontal? Sometimes one way will be easier and make your integrals easier to evaluate than the other. All right, questions so far? So that's all I want to talk about today. We're going to do a lot of things with these iterated integrals. So for today, I just wanted to introduce the idea and get to the concept of evaluating them inside out, and you could be able to practice a little bit with evaluating these iterated integrals. All right, there we go.